four ways to measure the average: mean, median, mode, and midpoint. And likewise, there's different ways to measure how spread out the data is. So you had an example in the last class, Malik. Do you remember which one you said? Yeah, you said maximum minus minimum. Do you remember that? And that's called the range. So one way, yeah, let me just plug this back in. Okay. So, oops. So imagine we have our data. So this is our data here. And we have different points in it. And we imagine that the average is some point in the middle. We'd like to know how spread out our data is. So for example, say we have numbers like 5, 2, 1, 6, 6, 8, 10. One way to measure how spread they are is to take the biggest number and the smallest number and minus them, 10 minus 1. This is actually called the range. And it's maximum minus minimum. But this is not the best way to measure because if I just add in an extra person here of 100, what happens to my range? It becomes a lot bigger, doesn't it? And all I've done is added in one extra point, which is far away. So we have another way to measure how spread out our data is. So we don't use range, we use something called the standard deviation. Okay, so what is the standard deviation? When we have data x1, x2, all the way up until xn, the standard deviation is the square root, the difference each point is from the average, squared, divided by the number of points, data points. This is called the standard deviation. Now, we'll do an example of a calculation and we'll explain what it represents in a minute. Yes?
Do you minus this from each point?
Yeah, and the order doesn't matter. So if you want to write it average minus x, that's fine as well. Yeah, I'll show you an example. What's what? This symbol here is a Greek letter called sigma. It's a Greek letter. It looks like this. Sigma. You remember in Greek, just like in English, you have small and big letters. So for example, in English you have A and A. In Greek, what's the first letter? Alpha. That's small alpha, big alpha. Small beta, big beta, small gamma, big gamma. And this one here, remember this letter? This is called sigma. That's big sigma. This is small sigma. Okay. So, Victor, that is supposed to be a sigma. Yeah. Okay, so let's have a look at an example. So, for example, let's say I have something simple like the numbers 5, 6, and 7. What's the average of 5, 6, and 7? 6. 5 plus 6 plus 7 over 3 is 6. You can calculate if you don't believe me, but it is 6. Let's calculate the standard deviation. So it's square root, and we have 3 numbers, and it will be 5 minus 6 squared. Actually, I'll color code it. Are my colors showing up? Let's see. I've got colors. 5 minus 6 squared plus 6 minus 6 squared plus 7 minus 6 squared. Alright, so that would be square root, let me see, 1 plus 0 plus 1 over 3. So that would be square root 2 over 3, which is 0.79 or something. Can you check? 0. I was close. 0.82. Okay, so now I need to explain what exactly does the 0.82 mean. So when you're ready, I can go down. Yep. Can I scroll down?
Yeah.
Yes? Okay. So, sorry, Marcelo, you have this? Yeah? Yeah. So for example, I have, here's my data here. And here is 5, and here is 6, and here is 7. And what's the average here? It's 6. Okay, so the first number, how far is it from the average? How many units away is it from the average? It's just 1 unit away. And 6, how far is 6 from the average? Well, 0, it is the average. And 7, how far is 7 away? 1 unit away from the average. So what is the average of 1, 0 and 1? Well, it'll be 2 over 3, which is 0.67. 2 over 3. So I know it's not the same because my data is so small, but the standard deviation is roughly the average distance each point is from the middle, from the average. So if you take the average of 1, 0, 1, this here should be about the same as the standard deviation. Now, it's not ever going to be the same. And the more n you have, the bigger n is, the better this is. So for only 3 points, it's not too bad. What did I get previously? It was 0.82. But for 100 points, then they're nearly the same, basically. So the standard deviation is a way to measure the average distance each point is from the center. Okay? So you're saying here, most points are this far away from the center. Do you understand? Yeah? So this is called the standard deviation. There's another formula for standard deviation which I want to show. Can I scroll down? Yeah? Yes? Now just before I show you, I want to give you some notation. This here is another symbol that I sometimes use for the mean average of x. So what do you think this means? Well, this is just the mean average ... squared. Oh no, not yet. But is that okay? That's fine. So what do you think this means if I put the square inside? What do you think? Yeah? Go on. Don't be shy. No? Got shy? Yeah. Anyone else? No? Everybody shy? No guesses? Or what they think that means? Yes, that's exactly it, yeah. So what you do is you square x first, then mean it. I just made a verb. I don't think mean is a verb. I just made it a verb, okay? So then mean it, average it. So can you see there's a big difference between these two. Here you get the average and then you square the answer. Here you square the data, then you get the average. So for example, if I had 1, 2, 3, what's the average here? 2. But for this one, oh, and the average squared would be 4. Now if I had 1, 2, 3 and I wanted this one, first I would have to change it into 1, 4, 9, and then I would get, let me see, 14 over 3, whatever that is. What is it? 4.67, 4 and 2/3, yeah. So you can see they're a little different, can't you? They're not the same, right? 4 and 4.67. So I just wanted to show you the symbols before the next part. Can I scroll down? You understand the difference between these two, I hope. Okay. So this formula for standard deviation, it's a little bit difficult. Let's see if we can simplify it.
What's the purpose of this one the root?
The square root,
Yeah.
is it? Without the square root is to make your answer be roughly the same as the average distance. Without the square root, your answer is too big. So it's just to make the approximation good, that's all. It's not really too special. And in fact, a lot of people actually calculate this and they don't use the square root, so it's not a big deal. Okay, so let's try and simplify this. So for the moment, I'll square both sides to get rid of the square for the moment. So here I have sigma squared equals sum xi minus x average squared over n. Next, I'll open the bracket. So this will be sum xi squared minus twice xi x average plus x average squared all over n. Okay. Now let me clean this up a little bit. You'd have the sum of xi squared over n minus the sum of twice xi x average over n plus the sum of x average squared over n. Okay, so we can clean up things a little bit here. This here, you square first or last here? Do you square at the beginning or at the end here? At the beginning. And then if you add and divide by n, this is a mean average. Is it the mean average of x? Not quite. It's the mean average of x squared. Here you square the x's and then divide by n. So that's okay. Now we need to simplify these. So I'll show you a trick to simplifying here. So imagine that you have something like this. ax plus ay plus az. What's in common here? A. So can you take a out? Yeah. So here, in the second one, what's in common every time? If I write this out, look at it, it'll be like this. 2x1 x average plus, if I write it out, sorry, 2x2 x average plus 2x3 x average. 2x average is in all of them. So what can I do with that? Well, I can take it out. So I'd have minus 2 average of x, xi over n. Now what's in average, what's in common here in the last one? Yeah, x average. If you look at the last one is x average squared plus x average squared plus x average squared. These are all the same. It's a constant. So I can take it out again. And what am I left with inside? Just like a 1. So if you have, for example, A plus A plus A, and you take out A, what are you left with inside? 1 plus 1 plus 1. So you're just left with 1. Okay, have a look here. What is this thing here? Add the x's up and divide by n. What is it? The average. And the number 1 plus 1 plus 1 plus 1 plus 1 plus 1, what is this piece here equal to? N. So you can cancel this. Okay. This here is the... Yep. Cancel.
Yeah, the 1.
1 plus 1 plus 1. If I have n of these, if I have 3 of these, what do I get? 1 plus 1 plus 1? 3. If I have 4 of them, I have 4. So if I have n ones, and I add them together, what do I get? I get n. So I can cancel the n here with this one. This one is twice the average of x, then I square, and the one at the end is plus the average of x squared. What do I get here? 1 of these minus 2 of these. So I get standard deviation squared equals average of x squared then averaged minus x averaged then squared. So this is another formula you can use to calculate the standard deviation. In fact, this is more common. It's a little quicker to use this formula. What I'm going to do is I'm going to do the same example again, but using this formula to show that you get the same answer. Oh, and of course, this should always be bigger than 0. You made a mistake if it's less than 0. You have this written down, yeah? Where's my first example gone? What numbers did I use? 5, 6, and 7. So let's use 5, 6, and 7 again, and let's see if we get the same answer. Okay, so we have 5, 6, and 7. This is our x data. What's the average of x? Well, that will be 5 plus 6 plus 7 over 3, which equals 6. So what's the average of x squared? That is 36. So the mean average squared is 36. That's fine. Now, if I want to do the next piece, well, I need to calculate x
25.
squared. Yes, so that's 25,
36.
36, and
49.
49. So the average here, squared, and then the mean average, that will be 25 plus 36 plus 49 over 3. Does somebody have that? 36.67. Okay. So we have this squared equals 36.67 minus 36. So if you do that, and then a square root, what do we get here? Nice. 0.82. The same answer. This method, this formula is much more convenient when you have many, many, many x values. It's just much quicker to do. Yeah? Okay, so I'll give you one example and then I want to show you one with a table. Can I scroll down? Yes? Okay. I'll give you 5 numbers. I won't be too mean. All right, no need to uncover. Right, so let's say our data is, come on, there we go. So we'll say 23015. So this is our X data. Let's make it. Okay, so you can use the first or the second formula, I don't mind. I want you to try and calculate the standard deviation for this X data. Yeah.
So in the exam, will we be marked on the standard deviation like the answer, or like how we, if we get the working out wrong or something?
Yeah, no, it's a bit messy and complicated in the exam, but basically you have marks for the method and marks for the accuracy. So the method will get you a mark, and then successful accurate calculation will get you another mark as well. So at the moment there are more marks for accuracy than method. So yes, you'll get some marks if you get the method, but the accuracy will be important, especially for the statistics question. Yeah. How are we doing? We have an answer?
Can it be like 2.96?
Certainly can, yes. You got an answer as well? Same as him? Yes? No, impossible. What? You have an answer, Tony? 1 point. Okay. I don't know, Tony, everybody's getting 2.
1.7.
Oh, okay. Hang on, which formula did you use? Victor and Tony, first or second formula?
Second.
And which, I know what you changed your tune. Sorry, Malik, everybody's changing their mind. Everybody's going for 1 now. Which formula did you use, the first or the second?
Second.
Okay, let's see what the right answer is then. Right, so first I'll get the yeah. Right. Sum.
I forget to get the rule.
There you go. Sum divided by 5. So did you get an average of 2.2? And then if you square this, you get this number squared, so you get 4.84. Now for the next calculation you'll need x squared data. So that would be 4, 9, 0, that's not 0, 0, 1 and 25, yes? Right, so we'll need this bit next. So that would be sum of these numbers divided by 5. So my standard deviation squared is equal to this minus this, 2.96. So the standard deviation will be the square root of this number which is 1.7. Somebody said 1.9. No? 1.7? In the exam, they would want the answer to be to 3 significant figures, so that would be 1.72. Okay. So we can get calculation of standard deviation, that's okay. Now let's have a look at an example with a table. Do you still have the table I gave you from the last class with the trees? Can we just write them down again? So we have height in centimeters and frequency. So what were the... okay, 0 to 9, 10 to 19, 29, 30 to 49, and then 50 to 99, and then here 2, 3, 4, 1, like this. So this time I want the standard deviation. Okay, relax. 2, 4, 3, 1. Now, do you know the average? We do. We got it last time, didn't we? What was it? What was it? The mean average. 28.05. So, can we know what this is? If we square it, what do we get, please? Thank you. 7. Okay. So if you want to calculate this, what do we need to calculate? Well, we need to square the data and then mean average it. So if we look at our midpoints, what was the first one? It was 4 point... Yeah, so our x is 4.75. Next. Yeah. 39.5. Okay. Right, so this is our x data. So what would you need to do? Yeah, you need to square these numbers and then take the average. And wait, before you do that, don't forget you have f's here. So what does that mean for your calculation? Each of these get multiplied by their f values. Yes, okay, try that, see what you get. I'll get my calculator too. Did you get an answer, Marcelo, for the x squared part? What did you get? Too big? 1179. Yeah, it's... Yeah. Why do you sound surprised? 1179.7125 is what I got. Yeah. So we have sigma squared is 1179.7125 minus 786.80. So if I get rid of that and put in this,
it's not 0.125.
It could be. I don't know. Point.
11,
Did you forget to divide by 10?
Oh, I think
Yeah. Right, so we square root this, let's see what we get. Minus 786.80 square root the answer, and we get 19.8. Okay, you have that? Yeah. So if you want to picture what that means, what was the mean average we got for our tree? What was it? 28.05 centimeters. So what that means is, if you were to look at the difference between each tray and the average, so here's the average across here, so there's a big difference here, a small difference here, and then maybe I'll go over here, and this one's a tall one. There's a difference here. If you were to get the average of these numbers, it will be 19.8 centimeters. So it's like saying each tray is on average 19.8 centimeters away from the mean average. Some trees, of course, will be more than the average, and some trees will be less than the average, and some trees might be the average. But on average, they'll be 19.8 centimeters away. Yes? I know I'm using the word average a lot, like Smurf or something. Can we get the idea for standard deviation? Yeah. So for something like income, do you think standard deviation will be big or will be small? It'll be big. What about something like height, people's height? Yeah, because most people are near-ish an average height. What about something like grades, student grades? Depends, yeah. But this class maybe. I think it's quite small. Most people are near the average for the class. Some, of course, more, and some, of course, less. And some, of course, not here. Yes. Okay. Anything else you might need to know about standard deviation? Sometimes, I think I'll do it with this one. Do I have the... No, I'll go back to my spreadsheet here. Yeah, okay. Standard deviation was 1.72. Oh, I lost it. What was the mean here? I can get it back. Do you have it? What was it? 2.2. And the standard deviation? Okay. So if you look at the mean minus one standard deviation, that would equal this number minus this number. And then if you look at the mean plus the standard deviation, that would be 2.2 plus this 2.2 plus this number. So can you just picture that in your head? 0.48 to 3.92. Picture those as two ends, okay? Is this number within that range? It is, isn't it? So we'll say that's in this number, in this number, out. Yeah, this one in and this one out. So how many are in and how many are out? There's about 60% are in, and then 40% are out. Do you think that's true for all data? That 60% of the data is within one standard deviation. So what I mean by that is, let's take our example of the trees. What was the average height of the tree? 28.05. The standard deviation? 19.8. This is called within one standard deviation. Do you think this is some rule that 60% of the data is always within one standard deviation? It's not a rule, but it's usually true for normal data. So in fact, most of the time this is true. For normal data, about 60% will be within one standard deviation and 40% will be outside one standard deviation. This is something we'll talk about again later, but I just want you to see the idea now. So, this means, as a very, 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 very rough rule, you can say that the standard deviation is roughly the range divided by 2 as well. Roughly. What's the range here? What's the biggest number? It's 5. And the smallest? 0. And what is 5 divided by 5 minus 0 divided by 2?
2.5.
2.5. Now, is that the same as the standard deviation? No. No, it's 1.72, but it's close. That's what I mean. Roughly, the standard deviation is half the range. No, sorry, hang on. No, I misspoke. I apologize. Not a half, sorry. Maximum minus minimum, quarter of the range, not half. This is something that we will see later, but I'm telling you now that's roughly a quarter. Right, that's not really any better. 1.25 and 1.72, but I mean it's pretty close. Now, wait, don't pack up. We've still got like 3 minutes left. So remember, the reason I'm telling you this is because sometimes it's good in your head to get a very quick estimate of some information about the data. So for example, can I delete this? Suppose I have this data. 5, 1, 2, 3, 4, 5, 1, 6, 7, 10. If I ask you to get the mean, that would take you a minute, right? But roughly, you can estimate it from the mid-point average. So what's the biggest number here? 10. And the smallest? 1. 10 plus 1 is 11, divided by 2 is 5.5. And what's the biggest number? 10, and the smallest? 1. So 10 minus 1? 9, divided by 4? Yeah, 9 divided by 4, 2.25. So I'm estimating the mean and standard deviation to be this, in my head, roughly. Let's see how good that was. I'll use the program to get the mean average. So the mean average was, not bad, 5.1, and we said 5.5. So, it's a good, quick estimation. And the standard deviation, let's see, I think it's SD maybe. SD, let's see if that works. Hang on, I'll get it. It's going to be called something like standard something. ST dev, there we go. It's not bad, is it? I mean, for something that you did in your head really quickly. The reason this is important skill is because in the exam, when you calculate the mean and standard deviation, you need to just take 1 second to think if your answer seems like it could be the right answer. So if you got an answer of 5.1 and you estimated 5.5, you should feel like you got it right. If you estimated 2.25 and you got 2.77, again, you should feel like you got it right. If you got an answer of 25, then what do you need to do in the exam? Go back and check your work, because it means maybe you did something wrong. Are you doing that thing where you're not listening to me anymore, right? Now, it is important that you try these, okay? So, I know they'll take some time to do because there's lots of calculator work, but it would be great if you could do everything on the page. We'll see next time. Try to do as many as you can, please. All of them would be great. Alright, let's wrap it up.